Hello folks and welcome back to The Shack. This is Joe N2DI coming to you today with the first of a long-awaited series on the NanoVNA. I've been getting tons of your requests for videos on how to make different kinds of measurements with the NanoVNA. Unfortunately, my day job keeps getting in the way of fun time for me, as I'm sure is the case with most of you, unless you're lucky enough to be retired. So I'm going to try really hard to get out a useful series of videos for you on the NanoVNA, and I appreciate you all being very patient. I'm kicking off this series with a few types of coax measurements you can make with your NanoVNA. I'm going to try to make a video on everything that I've seen requested so far, but if I miss something that you uncovered, then please just ask in the comments. Okay, if you're ready to learn how to make some useful coax measurements with the NanoVNA, then let's get started. The first thing I want to do is make sure that we're all on the same page. I'm using the NanoVNA H4 with the Dislord 1.2.46 version of the firmware. Second, I'm going to recommend that you pick up a few adapters to help you get from the SMA connections on the NanoVNA to your coax. I recommend getting a couple of SMA male to BNC female and SMA female to BNC female. I would also get a couple of SMA male to SO239, which is basically the female version of a PL259, and an SMA female to SO239 female. This will allow you to directly connect your coax to the ports of the NanoVNA for an S21 measurement. It will also allow you to connect a terminator or a short to the other end of your cable by using the short and terminator that comes with the calibration kit for your NanoVNA for things like S11 measurements. Now, if you don't know the difference between an S11 and an S21 measurement, then watch my video, NanoVNA, all the little stuff nobody explains. I go into more detail there. Now, with those adapters, let's get started making some measurements. The first type of measurement we're going to make is to measure the loss in your coax. Some hams may not know the two most important factors that impact the loss in your cable. Those are, number one, the length of your cable, and number two, the frequency that you're using. Now, passing your signal through anything is going to introduce loss, and coax is no different. Now, there are different types of coax that may have more or less loss per length unit that the cable is measured in. So, for instance, it may list the loss in decibels per 100 feet. Regardless of what that is, the longer your coax, the more loss you're going to have, because your signal has more cable that it has to pass through. So generally speaking, keeping your coax as short as possible is usually better. Now, the second and not so obvious thing that impacts loss is the frequency you use. A piece of coax may be perfectly fine for HF frequency, but as you move up into VHF and UHF frequencies, you'll see that the losses become greater and sometimes unacceptable. So how do we go about measuring this? A piece of coax may look perfectly fine, but when you test it, it can be complete garbage. What we're going to do is an S21 measurement. That means we're going to send the signal out of port 1 on the NanoVNA through your coax and measure what comes in on port 2. Okay, so the first step we're going to do here is set the start and stop frequency to something that makes sense for how you intend on using your coax. If you're going to use it for HF, then you can set your frequency range from, say, 50 kilohertz to 30 megahertz. If you're going to be testing for VHF and UHF, set your range to something like 50 megahertz to 500 megahertz, or even 50 kilohertz to 500 megahertz. And make sure that you're scanning with 401 points to get your highest resolution. Okay, I'm going to set my frequency range with stimulus, start, 50 kilohertz, stop, 500 megahertz. Now, after setting the frequency range, you have to perform a calibration. You need to do a full calibration since this is an S21 measurement. That means you have to do the open, load, short, isolation, and through. Now, I'm going to zoom in a little bit more here so you can see a little bit better. All right, now to do the calibration, we want to go back to the main menu and hit Calibrate, and then reset to clear out what calibration is already set there. Then we'll hit Calibrate, and we'll start with the open. Okay, so now I'm screwing on the open part of the calibration kit. And we'll hit open, let that do its thing. Now we need the short. And by the way, you can tell the difference between the open and short because when you look inside the cap, you'll see it has no pin, and the short will have a pin. Okay, so we'll screw that on. Short. Now we need the load, which is basically 50 ohm dummy load. Hit load. Okay, now for isolation, we're going to remove that 50 ohm load and we're going to put it on port 2. And the point of this is to prevent any stray noise from the environment from getting into port 2 during the isolation test. If you have 2 of these 50 ohm loads, then you could screw them on both ports. I only have 1, so I'm going to put it on port 2, hit isolation. Okay, and now we have to do the through calibration. Now for the through, I have a short piece of RG 405, that's low loss, and I'm going to screw that on. Okay, now I'm going to hit through. Now I'm going to hit done and save that to this memory slot here. I'm going to overwrite this 50 kilohertz to 500 megahertz. Okay. Now we'll disconnect that through. And if you ever want to check your calibration, if you have the Smith chart being displayed, an open will put a marker here all the way on the far right. A short will put one all the way on the far left. And the 50 ohm load should land right in the middle. So here now that there's nothing connected to port 1, we see the markers all the way over to the right. I'm going to put on the dummy load real quick. So with the 50 ohm load attached, there it is. The marker's right in the center. That's 50 ohms. Okay, and the short. And now the short, the marker's all the way over on the left side. So now if you do your calibration and you test that and that doesn't happen, one of those doesn't land where you would expect it, I would just redo the calibration again. But normally if you've done the calibration correctly, it'll just wind up that they'll land in the correct spots. Okay, so the next thing we're going to want to do is set your display to only have one trace, and it's going to be a through measurement, an S21 measurement, and we're going to set the format to log magnitude. Okay, so we're going to go to display, trace. We're going to turn off this second. The first, we'll use 0. Whoops. Turn off that one. Back out. Okay, now we're going to set the format to the through, an S21 measurement, and log magnitude. Okay, so now that yellow trace is going to be log magnitude. Now, log magnitude is what you use when you're trying to measure the loss through something like a cable or an attenuator, or you're trying to characterize a filter or something like that. It's going to show you the loss between ports 1 and 2 in decibels. So the closer the line is to the top of the screen, the less loss there is. Okay, I'm going to zoom back a little bit here so it's easier for you to see what I'm doing. And I'm going to connect those adapters to ports 1 and 2. Okay, these are the SMA male to BNC female because I'm going to be using a piece of BNC coax. It has BNC connectors on both ends. Now, obviously, if you have PL259s, then you're going to want to have the SO239 version of this, which would just be the SMA male to SO239 female. Okay, so now with those both connected, we're going to connect both ends of the coax. I got a spool here of about 25 or 26 feet of RG316. So we're going to connect both ends. And we're going to take a look. Now let me zoom in a little bit here. What you have here now is the loss in decibels. Now I'm going to move the marker by using the little jog switch at the top here to slide it around. You can add multiple markers. You can use one marker and move it around. You can actually click and drag that marker. Let me see if I can do that and move it around. Whatever. I'm just going to use the jog wheel here just so my hands are out of the way so you can see the display. So if you look at M1, it's going to show you the frequency that you're at. And then the yellow S21 measurement is showing your loss in decibels. So you could see at 50 kilohertz, the loss is only 0.1 decibels. Now, as we slide that along, let's get to the top of the HF band, which is like the 10 meter, around 29 megahertz. You can see that the loss there is 1.05 decibels. Not great, but it's not the end of the world. I mean, it's still usable at that frequency. But now the problem is, let's look at some higher frequencies, right? Let's look at 2 meters. Now at 2 meters, you're at minus 2.4546 decibels. It's hard for me to see in the monitor here. About 2.45 decibels. That's significant. Minus 3 decibels is a 50% loss in power. So that's significant. And now look, as we get up towards the 70 centimeter band, your loss is minus 4 decibels. You're losing more than 50% of your power. So RG316, you could use it for HF, but I would not use it for VHF and UHF. Now, just as a quick comparison here, I stuck a piece of LMR 240 Ultraflex that's about 30 feet long, 29, 30 feet long. And the loss at 29 megahertz up in the 10 meter band is only about 0.5 decibels, which is much better than the RG316. And we could look at the VHF portion here, around 2 meters, 1 decibel loss. And up here in the 70 centimeter portion, we're close to 2 decibel loss. So not great. I mean, I'd probably use LMR 400 or something here if I was going to be using UHF if I wanted to reduce the loss more than this. But that's just a quick comparison between RG316 and LMR 240. The next test we're going to do is a test to measure the length of your coax. Now this test uses Time Domain Reflectometry, or TDR. Now the reason why I'm telling you this is so you could pull that little tidbit out at your next party and impress everyone. Now to do this, you need to know your coax's velocity factor. Now what the heck is your velocity factor? Well, normally your signal, if we were traveling in a vacuum, would travel at the speed of light. But since your signal is not in a vacuum, it's in your coax, then your coax is going to slow down your signal some percentage of the speed of light. So that is your velocity factor. So if your coax's velocity factor is, say, 0.66, then your signal is traveling at 66% the speed of light in your cable. Now, the reason why that's important is this test sends a signal down your cable, which hits the open, then reflects back to the NanoVNA. Now, the NanoVNA is going to time how long that takes, and it calculates the length of your cable based on that velocity factor. So if you have the wrong velocity factor, your NanoVNA is going to give you the wrong answer. I'm sure your next question is going to be, well, how do I get the velocity factor of your coax? Well, the best way to do it is to look up the velocity factor at the manufacturer's website, or just Google it. You'll see that they're usually the same. So for instance, LMR 400 is 0.85, LMR 240 Ultraflex is like 0.80, RG316 is 0.695, but you could round that up to 0.7. So since this measurement measures the time it takes a signal to leave port 1 and be reflected back to it, then this is just an S11 measurement. Oh, the other important thing to know is all these measurements are done in metric, so you have to convert if you want to convert to feet and inches. Okay, so now the first step is to set the frequency range. A higher stop frequency will give you better resolution, meaning a more accurate distance, but a lower stop frequency will allow you to measure a longer cable. So you can use this formula to estimate the stop frequency that you'll need. So your stop frequency in megahertz will be 5,850 divided by the expected length that you want to measure in meters times the velocity factor. So for example, if you wanted to measure a 30-foot length of RG316, 30 feet is about 10 meters. And the velocity factor is about 0.70. So 5,850 divided by 10, and then times 0.70 will give you 409.5. Okay, so then your stop frequency would be 409 megahertz, or around there about. For 100 feet of LMR, your stop frequency would be 5,850 divided by 30 times 0.85, or around 165.75, or about 165 megahertz. Generally, you're going to be using higher frequencies for shorter cables. So the first step is to set your frequency range and then do a calibration. Now, since this is only an S11 measurement, you just need to do the open, short, and load part of the calibration. I'm just going to use the existing calibration that we did earlier to save time. Okay, next you're going to want to set up your display. Now you only need a single trace for this test, and the format should be linear. So here we'll go to display, trace, we'll turn off 2 and 1. We'll go to 0, and we'll set that, make sure it's S11 because it's a reflection measurement. And we're going to go to more, and then linear. Now we can back out of that. Now the next step is you're going to want to turn transform on. And set this to low pass impulse. Now in the transform menu here, you're also going to want to set the velocity factor. So you're going to set it as a percentage. So if your velocity factor is 0.66, you're going to key in 60%. I'm going to measure RG316, which is 0.70 or 70%. Okay, now we're all set up. Now all you need to do is connect the cable to the S11 port and leave the other end not connected. Okay, now you're going to get this spike on the screen here. Let me center this, sorry. Okay, you're going to get this spike. So now that spike will tell you the length of your cable. Now you're going to want to move your marker over to that spike. There's an easy way to do it. The most accurate way is go back to the main menu here, pick marker, and then you want to search for the maximum. So you tap that twice, and it'll automatically jump there. Now you can see the length is 8.034 meters. Now I'm just going to type that into Google real quick to see. 8.034 meters to feet is what? That's 26.35 feet. So that's about 26 feet 4 inches and change. Now I'm going to disconnect this RG316 and I'm going to put that LMR240 on it. Now the velocity factor for that is different, and it's a slightly longer piece of cable, so let's see the difference. Okay, now we can see it says 7.87 meters, but the velocity factor is wrong. So let me correct the velocity factor and let's see what happens, how much we could be off by. So the velocity factor for LMR 240 is 80%, so it's 80%. Now look at that, that was pretty significant. So now it's 8.995 meters. Our quick check on Google says that's 29.5 feet, which is correct. Okay, so that's how you measure your coax length using time domain reflectometry. Don't forget to use that at your next party. All right, the last test we're going to do is to figure out what your velocity factor is, and you can do that if you know the physical length of your coax. So if it's a measurable length, then you can calculate your velocity factor. Now this test is another S11 test, so you just need to do the open, short, and load part of the calibration. So the steps are, first, measure the length of the cable. Okay, now I'm using this shorter piece of cable because it'll be a lot easier to demonstrate. This cable is actually 547 millimeters long. Because it's so short, we're going to get an answer that's in millimeters. So I measured in millimeters, it's 547. Now you're going to want to connect the cable to the S11 port. This cable has SMA connectors, which makes things easier. Or maybe not. Okay, so I'm going to zoom in a bit here. Okay. Now you're going to set up your display the same exact way that you did when you're measuring length. So you only need one trace. You want to turn on transform. You want to set this to low pass impulse, and your velocity factor. Now, if you're trying to figure out what your velocity factor is, you're going to set this to 100%. Okay, now you want to take this reading that you have here, which is 781 millimeters. Now, to get the velocity factor, what you're going to want to do is take the physical length and divide it by this electrical length. So the cable's actually 547 millimeters. And if I divide it by the electrical length, which is 781 millimeters, I get 0.70034, blah, blah, blah. So it's 0.70 is the velocity factor. Okay, so again, the velocity factor is the physical length divided by the electrical length. Okay, folks, so that's it. That's how to make some interesting coax measurements with your NanoVNA. Stay tuned for more NanoVNA videos, hopefully coming soon. I'm going to try to get to all of your requests that have come in so far. I hope you found that useful. So from the Shack of Joe, November 2, Delta, India, I wish you all good health and 73. Bye-bye.